Good morning. My name is Ernesto Iglesias Rodri, and I am a PhD student at Autonomous University of Mexico. Now I am part of the SIAM students chapter, and at the end of this presentation I will talk to you a little bit about that. I want to thank you all to be here, and the work I'm going to present is entitled Reiterated Homogenization with Application to Nanofluids. We will start with an introduction. We focus mainly in the method of asymptotic homogenization and in the numerical approach employed to solve some differential equations. And finally, we are going to see some results and the conclusions. A nanofluid, as the name implies, is a fluid containing a nanometer-sized particle, and they are very new and have a lot of application, in particular for heat transfer application. There is an increasing interest in the phenomena known as gain in thermal conductivity, compared with the gain of traditional colloid. Recent studies have shown that this gain is influenced by the formation of conglomerates. As seen in the picture, they form a conglomerate of a scale higher than nano size. Nanofluid can be seen as a very complex composite material in terms of continuum mechanics. For modeling purpose, we will consider two possibilities, which differ in the form we deal with underlying information of the dispersed phase. The model 1 consider this dispersed phase as a part of the matrix, and 2 considers it inside the envelope of conglomerates, and this envelope is considered as an individual part inclusion. The determination of macroscopic properties of composite material by mathematical methods is a fundamental requirement in the research and study of materials with complex structures. The field of study of this subject is called homogenization. And reiterated homogenization refers to the consideration of several scales in homogenization. The mathematical models that result from homogenization require the solution of boundary value problems, and the analytical solution of this problem can only be achieved for certain inclusion geometries of the periodic cell. However, in general, it is necessary to apply numerical methods to solve such problems, and that's why our objectives were to apply the reiterated homogenization method to conductive media, considering 2 microstructural scales and a thermal barrier in the interface, and finally to use the finite element method to calculate the effective conductivity of some classes of this media. The boundary value problem is an elliptic one, also referred in the literature as the Fourier heat problem, where the coefficient A is a conductivity tensor, which is periodic inside the cells, and the rapidly oscillating character is given by a parameter of small size. In this example, we can see how even for simpler expressions with continuity, etc., of the coefficient, the medium gain in complexity as the small parameter tends to 0. As in the figure, we have an epsilon. But we are going to consider a more complex materials formed by multiple phases, and each phase is connected with each other, as in matrix and inclusions, and in the boundary, in the contact between these phases, we are going to consider an imperfect contact, also called thermal barrier, and we are going to use the Biot number to refer to the conductance. Biot number is adimensional, and when tends to infinity, it means that the contact between phases is perfect. The asymptotic homogenization method provides mathematical models that allow the calculation of effective properties of a composite. What we have is it allows to convert a problem with rapidly oscillating coefficients with in a problem, a new one that represents the behavior in a global sense, but with constant coefficients. Formally, what they do is to represent the solution as an asymptotic series with periodic coefficients, a series of epsilon exponents. And in this manner, we can derive the effective coefficients, and in our case, as we have two scales, we are going to have two coefficients, one for the larger microstructural scale and the other one for the macroscopic scale. Each one will depend on a local function that is defined on the periodic cell of the previous scale. And this local function responds to what is called local problems. These local problems have a similar form and heredate the discontinuities of the original problem. These problems are needed to obtain the effective coefficients and are hard to obtain the solution. That's why we need the numerical methods, and in particular we choose the finite element method, because finite element methods allows to obtain an approximate solution of the differential equation based on a structure of nodes and elements, so the solution reduced to solving system of linear algebraic equation. Another advantage is that the problem the differential equation will be in the weak forms. It is an advantage because we can use more general functions that just require continuity and some kind of derivative. To incorporate the contact condition on the interface, we will use the technique of domain decomposition method. This consists on an iterative process that alternatively solves the equation in subdomains formed by matrix and inclusion. In this form, we have to obtain solution for different problems in different places, but with a common frontier, a common boundary, and this common boundary is the way in which the information will be shared in the iterative process. So for solving in the interior, we need to know a solution in the frontier of the exterior, and like this. And each one of these problems can be solved individually in finite element method software. As a matter of validation, we compare with non-results for circular fibers. In fact, it's interesting that using analytical known solutions, applying two scales escape from the theoretical lower and upper bounds of the literature, while our method doesn't. With this validation, we pass directly to solve some different problems. Here, for example, we have different fiber cross-section shapes that were solved using this scheme of asymptotic homogenization method combined with finite element method and domain decomposition method. And we want to know how these shapes affect the effective coefficients. In fact, for higher roundness, it can be seen that there is a higher value of these coefficients. Phi represents the concentration. To conclude, we can see that the employed scheme demonstrates the ability to solve several complex structural problems. The computational implementation was calibrated through comparison with other theories, either analytical and variational, and we can also compare the effective behavior of fiber reinforced media with several microstructures. We are working to expand this study to a three-dimensional composite, generalize the form we introduce these geometries using computer-aided design software, because this is just the first step for the study of the influence of the geometric characteristics, and we need to compare the obtained gain with experimental results. Here I have some reference used for this presentation, and I want to acknowledge the support of CONACYT and UNAM, the project Papin de Gapa Nam here shown, and the Brazilian Society of Foresting Agency CNPq. And special thanks to SIAM to allow me to be here, and best regard to its recently opened student chapter that have started past month. Here I have the email of the student chapter if you want to communicate with them, join if you are a student, or ask question, anything. Thank you very much.